All right, it's time to move on to section 3.3, trigonometric substitution. This stuff is really neat. This is one of my favorite things in Cal 2, and so I'm very excited to share this with everybody. Before we start this, there is one thing from Trig I want to very quickly review because it's going to be something we are going to need for this. And so what that's going to be is that if I have something like, if I tell you for a fact that sine of theta is equal to like x over 4. Okay, let's say I'm telling you that, and I want to know what the other trig things are, right? So I want to know now, what is cosine? What is tangent? What is cosecant? What is secant? What is cotangent, right? I want to recap how I do that real quick. So if I know what sine is, remember our rule for sine is that sine is equal to opposite over hypotenuse, right? So what this means is if I have a triangle, and I'm using this guy right here, if I know what the sine is, I know what this side length over here is, and I know what the hypotenuse is. I know since it's opposite over hypotenuse, opposite must be x over my hypotenuse, which must be 4. Therefore, I can find this side length over here using the Pythagorean theorem. Remember, leg squared plus leg squared is equal to hypotenuse squared. So this side length I don't know squared plus this side length I do know squared must be equal to 4 squared. So I can move the x squared over there. So the side I don't know squared is 4 squared, which is 16. I can go ahead and put that, I guess. 4 squared is 16 minus x squared, and then take the square root. So this side length I don't know is a square root of 16 minus x squared. Now that I know what all three side lengths are, I can go through and find all of these. Cosine is adjacent over hypotenuse, so square root 16 minus x squared over 4. Tangent, opposite over adjacent, so x over square root 16 minus x squared. Cosecant is 1 over sine, so if sine was x over 4, cosecant would be 4 over x. Secant is 1 over cosine, so this would make it 4 over square root 16 minus x squared. Cotangent is 1 over tangent, so square root 16 minus x squared over x. So again, if I know what one of them are, I can use it to find all of my side lengths and therefore find everything else. This is a skill we are going to need for this class. Okay, so now I can get into the trigonometric substitution. Really quick, just like we did for our last class, we need these trig rules that say sine squared theta plus cosine squared theta is equal to 1, which means sine squared theta is equal to 1 minus cosine squared theta, or that cosine squared theta is equal to 1 minus sine squared theta. Either one of those is right. We also have the trig rule that 1 plus tangent squared theta is equal to secant squared theta, which means secant squared theta is going to be equal to, secant squared we already did. Tangent squared theta is going to be equal to 1 minus secant squared. Secant squared minus 1. Ooh, what is wrong with me? Bring the 1 over there. Secant squared minus 1. So these are going to be some trig rules we're going to use throughout today's class. Okay, now let's get into the trigonometric substitution. Really quickly, on the handout, I explain in words what I want to do. The thing with this is that I don't really like it in math whenever we just want you to like remember rules. You know what I mean? That's not the idea. I'm trying to really get you guys to understand the concepts. So instead of me going through these steps, I'm just going to work them to show you what it is I'm trying to say up here. But up here, this is a really good description of what I'm going to do, what the steps are. But again, I want to really show you guys why, how I get there, and that kind of stuff. So I'm going to focus more on the examples rather than the wording I have up here. And then what this is this is just a recap of what I had reviewed here, is what it is. So let's just jump right into example number 1. Example number 1 is the integral of the square root of 9 minus x squared dx. So using what I know so far, your first thought would be this is the square root of some stuff, right? So my first thought would be let's use u substitution with u equals 9 minus x squared. But in order for that to work, the du would have to be negative 2x dx, and I do not have an x here to use. So that doesn't work here. So instead, what I want to do is I want to see if there's another way I can rewrite this into something I can do, okay? So think about those trig rules I had written down. This is a constant minus something squared, right? A constant minus something squared. This looks a lot like when I wrote cosine squared equals 1 minus sine squared. It is a constant minus something squared. So I want to use this rule to plug something into here to turn it into a form that I actually can do. So the difference here, though, is that I have a 9 here, but I only have a 1 there. But I can make this a 9 by multiplying everything by 9. And that's good. So now it looks just like this. So what I want to do is I want to say, okay, what would x have to be to where I can use this rule, okay? Well, it's 9 minus something squared. Over here I see I have 9 minus 9 sine squared. So what would I have to square to give me 9 sine squared, right? Well, to get the 9, I would need a 3. So 3. To get sine squared, I would square sine. So I'm going to let x be equal to 3 sine. Again, because whenever I plug this in for x, it would be 9 sine squared, which means I can use this rule. Okay, so let's do that. Oh, and then also dx then, the derivative of that, the derivative of 3 sine is 3 cosine. So let's use all of this stuff to rewrite this guy. So this is going to become the integral square root of 9 minus x squared is 3 sine squared, quantity squared. 3 squared is 9, sine squared is sine squared, theta. And then this is a big step. Dx, I have now changed. Dx is equal to 3 cosine. So I have to put that there. Times 3 cosine theta d theta. Again, because that is what dx is. So now I'm going to see if this can help me, because right now it looks really gross, but I'm going to try to rewrite this so that it's not that bad. First things first, I have a constant of a 3, so I can bring that out front. 3 integral square root. Let's look at 9 minus 9 sine squared. Just like our rule said, 9 minus 9 sine squared is the same as 9 cosine squared, which is really nice. And then I have a cosine out here still. D theta. Why is this helpful? Well, because I can do the square root of 9. Square root of 9 is 3. And the square root of cosine squared is just cosine. So now I have another 3 in here. I can bring it out, making it 9. Integral cosine times cosine is cosine squared. So now this is a thing I can do. We had learned this our last class. Cosine squared, I would rewrite it to be using that trig rule. 1/2 plus 1/2 cosine 2 theta d theta. Take the antiderivative of that with a 9, or sorry, with the 1/2, that is just a constant. So this would be 1/2 theta plus the antiderivative of cosine 2 theta is 1/2 sine 2, because I would let u be equal to 2 theta. So du would have to be 2. I don't have a 2 here, which means I need to times it by 1/2. We did a lot of these our last class, right? Which would make this 1/4 antiderivative of cosine is sine. Plus c. Distribute my 9 in there. 9 over 2 theta plus 9 over 4 sine 2 theta. A lot of people see this and think I'm done. I did it. It's all great. But let's think about why I'm not done quite yet. That is because my original problem was dx, meaning I want what I get at the end to be in terms of the x. So I can't stop until what I get is in terms of the x. So I need something to plug into theta to give me in terms of an x. Well, if x is equal to 3 sine, I could solve this for theta by dividing by 3. So x over 3 equals sine theta. Again, I'm using this guy. And so to get the theta, this would have to mean that inverse sine of x over 3 is equal to the theta. So I'm going to plug this in for theta to make it in terms of the x. So this is going to be equal to 9 over 2 theta, which we just said was inverse sine of x over 3, plus 9 over 4 sine of 2 times theta, which is inverse sine x over 3, all that, plus c. So this is another one of those things, which I will say a billion times in this class, is that this is something where when you look back at what you did, you're like, oh my gosh, this was hard. But really think about what you did at each step, right? You really didn't do anything that's overly hard. First things first, I realized this was a trig rule, so I let the x be equal to 3 sine because I needed a 9. What do I square so that I get 9? You square a 3, so 3 sine. Doing that makes this 9 minus 9 sine squared, which is equal to 9 cosine squared, and the square root of that is 3 cosine, so that's not that bad. But remember though, I need to then replace dx, so I put that in there, 3 cosine theta. Took the 3 out front, cosine times that cosine gave me cosine squared. Our trig rule from section 3.2 was that I can rewrite cosine squared as 1/2 plus 1/2 cosine 2, which then I can take the antiderivative of and then make sure we plug back in what the theta was so that I have it in terms of the x. If any of that doesn't make sense, please let me know. I will help you out. I can stop here because there's no way to simplify all of this stuff, so I can just stop there. As we are going to see with example number 2, sometimes we can simplify things. So let's see about that. Example number 2. Example number 2 is the integral of the square root of 4 minus x squared over x dx. So same problem here. Your first thought would be I have the square root of stuff, so I'm going to use u substitution with u equals 4 minus x squared. But in order for that to work, du would have to be negative 2x dx. And initially you may think, oh, well, that's good because I have that x here. But this is an x in the denominator. I want it in the numerator. So that wouldn't work here. So I'm going to see if there's a trig rule I can use here. So again, I have a constant minus something squared, which means I can use that trig rule where cosine squared is equal to 1 minus sine squared. So I'm going to pick an x. I have a 4, which means I need a 4 there. What can I square and get 4? Well, that would be 2, right? 2 squared is 4. So 2, and then the whole idea is I want a constant minus sine squared, so it's going to be 2 sine theta. But again, don't forget, I need dx. The derivative of 2 sine is 2 cosine. So let's plug all of this in and see if it helps us out. So this is going to become the integral of the square root 4 minus x we said was 2 sine. So if I square that, 2 squared is 4, sine squared is sine squared, over the x, which we said was 2 sine, times the dx, which we said was 2 cosine theta. So this looks like a jumbled mess, right? But let's see if I can work this out to where it's not that bad. 4 minus 4 sine squared, that's a trig rule. This is equal to 4 cosine squared. What's really nice here is 2's cancel out. So that's out of there. Sine theta times cosine theta d theta. The square root of 4 cosine squared, the square root of 4 is 2. The square root of cosine squared is cosine. So this 2 I can bring out front from the square root of 4. Square root of 4 gives me 2. I bring it out front. Integral. Square root of cosine squared is cosine. Here I have cosine times cosine, so that becomes cosine squared. Now right here, a first thought may be, okay, now I can do u sub. So u would be equal to cosine, which would mean du would have to be negative sine, which again, initially looks okay, but then if I see sine is in the denominator, which isn't good, right? I need it in the numerator. So that still doesn't work. So I've got to rewrite this again using some kind of trig rule. Well, I know cosine squared is equal to 1 minus sine squared. So we can use that. 2 integral. Again, cosine squared is 1 minus sine squared. Since on top I have 2 terms there, I can split that up and do 1 over sine minus sine squared over sine. Why is that helpful? Because 1 over sine is cosecant. Minus sine squared over sine is just sine. So now I can just take the antiderivative of each of those. The antiderivative of cosecant is negative natural log of the absolute value of cosecant theta plus cotangent theta. And the antiderivative of negative sine is positive cosine plus c. But I can't stop quite yet because this is dx, which means I need it in terms of the x. I'm going to have to get another board. Since x is equal to 2 sine, again, since x is equal to 2 sine theta, I can divide it by 2. X over 2 is equal to sine. And so I can use that to figure out what cosecant is, what cotangent is, and what cosine is. So let's do that really quick. Sine being equal to x divided by 2 gives me that this side over here is x and this side is 2. Again, because sine is opposite over hypotenuse. So that's why. So I can get this side by doing the square root of my hypotenuse squared, which is 4, minus my leg squared, x squared. This is what I reviewed at the start of class. So again, what I need from these is cosecant. Cosecant is 1 over sine. So that's going to make this 2 times negative natural log. Again, cosecant is 1 over sine. If sine is x over 2, cosecant would be 2 over x, plus cotangent, which is adjacent over hypotenuse. So square root of 4 minus x squared over x, plus cosine, which is adjacent over hypotenuse. So square root of 4 minus x squared over 2. All of that plus c, and then now I can distribute my 2. So this would be negative 2 ln absolute value 2 over x plus square root of 4 minus x squared over x plus distribute my 2. This 2 would cancel out with that 2, so it's just a square root 4 minus x squared plus c. There's a negative out front. I wrote over it by mistake. There we go. All right, so again, since the answer I got was cosecant of this thing, cotangent of that thing, cosine, I've got to do what I did at the start of class, which was using what I know with the sine to get everything else. The reason I didn't do that on the last one was because I ended up with, I believe it was 9 over 2 theta. So I wasn't looking, I ended up with that. So I wasn't looking for like cosecant of a thing or cotangent, right? It was just 9 over 2 theta. So I could just stop right there once I plugged it in. Which gave me this. I believe it was x over 3. And then the other part was, I'm trying to remember off the top of my head. I believe it was plus 9 over 4 sine 2 theta. So this 2 meant that the theta I was trying to use isn't the same one. So I can't use this because it's 2 times that. So then this rule wouldn't work because it was 2. If there wasn't a 2 there, then I would be fine. But that 2 meant that I would just have to leave it sine inverse 2 inverse sine x over 3 and all that stuff. That's why on the last one I didn't. But this one is just saying cosecant of that thing, cotangent of that thing, on, which I can find using this. If that doesn't make sense, please let me know. I can explain it a different way or whatever would help you out. All right, so that's example number 2. If any of it does not make sense, please tell me. Example number 3 now. Is the integral of x cubed square root 1 minus x squared dx. This is x squared. Same thing, because I have the square root of some stuff, your original thought may be to do u substitution, but if I did that, u would be 1 minus x squared, so du would have to be negative 2x dx, whereas I have x to the third, I only want the 1x, and so that does not work here. So again, let's see if there's a trig rule I can use. I have 1 minus something squared. I know my rule is that cosine squared is equal to 1 minus sine squared. So for this one, I can just let u be equal to sine theta. Sorry, let x be equal to sine. Again, this is a 1, which means I just need a 1 right here. Had this have been a 9, I would have put 3 because I would do 3 squared, which would have to then be 9. If this was like 25 right here, I would do 5 sine because it's something squared, and on and on. But since I just have a 1, it's just 1 sine. Since x is equal to sine, the derivative of that is cosine, so dx is equal to cosine. Let's work on rewriting this. X cubed, which would be sine cubed, because that is x. Cubed, not squared. sine cubed theta, square root 1 minus the x's sine, so sine squared theta. Dx we're rewriting as cosine theta d theta. Let's work this out. 1 minus sine squared is cosine squared. So this is an integral of sine cubed theta, square root of cosine squared theta times cosine theta d theta. Well, the square root of cosine squared would just be cosine. Cosine times cosine is cosine squared. So this becomes the integral. I need to find a better way to write that. Integral sine cubed theta. Once again, cosine times cosine is cosine squared. And this becomes a problem like what we did our last class, where since I have an odd power for sine, I'm going to bring one of them out. Again, since I have an odd power for sine, bring one of them out, leaving me with sine squared because I had 3 of them. Now I only want 2 because I'm going to bring one of them out. And the reason why is because now I just have sine squared, which I know is 1 minus cosine squared. Times cosine squared times sine. And now I can use u substitution with u equals cosine, because du would then be negative sine d theta, which I have out here. The minus sign, remember, I'm going to bring it out front, so it's going to be negative integral. 1 minus cosine squared would be 1 minus u squared times cosine squared, which again is u squared. Sine theta d theta is now du. Just like we did our last class, this means I can distribute u. So this is going to be negative integral. U squared times 1 is u squared. U squared times u squared is u to the 4th du. Now I can just take the antiderivative of this. So negative, add 1 to the power, divide by my new power. Do the same thing over here to make this u to the 5th over 5 plus c. This is a u, so I need to plug back in what I said the u was. We said right here u is equal to cosine. So this means it's going to be negative, distribute the minus sign, negative cosine cubed theta over 3, minus would make it plus cosine to the 5th theta over 5 plus c. But I still can't even stop there because the original problem was in dx, which means I need this in terms of an x. We know x is equal to sine, which I could write as x over a 1, right? So on my triangle, sine is equal to x over 1, so opposite is x, hypotenuse is 1, which means this missing leg is the square root of my hypotenuse squared, well 1 squared is just 1, minus my leg squared. Cosine is adjacent over hypotenuse, which would be square root of 1 minus x squared over 1. So cosine of theta is just the square root of 1 minus x squared. So now I can plug this in to the answer, and you get negative square root of 1 minus x squared cubed over 3 plus, again, cosine is square root 1 minus x squared. I'm doing that to the 5th over 5 plus c. As I've said, and as I will always say, if any part of that isn't clear, please contact me and let me know. I will be happy to help you out. All right, let's go on and do some more examples. Example number 4 is going to be the integral of dx over the square root of 1 plus x squared dx. So for this one, inside of my square root, I have 1 plus something squared. So this plus means I can't do exactly what I have done, because in every other problem I've had, it's been something squared minus, right? Now it's plus. So think about our trig rules. We know that we have a rule where 1 plus tangent squared is equal to secant squared. So I have 1 plus something squared, which means I'm going to use this rule right here because it's 1 plus tangent squared. So what this means is that x is going to be equal to tangent. But if that's true, then dx is going to have to be secant squared d theta. So let's work this out. Oh, dx out front. We should only have dx one time. The dx is already here. If you see this, this is the same exact thing as having 1 over that stuff, dx. Either way, it doesn't really matter. I'll leave it like this. But like I said, it really doesn't matter. Oh, this is example 4. Sorry about that. So this is going to be integral 1 over square root 1 plus, our x is tangent. So this is tangent squared theta. Dx we just said was secant squared theta d theta. So let's see if this will help us out. 1 plus tangent squared is equal to secant squared. So 1 over the square root of secant squared theta times secant squared theta d theta. Square root of secant squared is just secant. So this is going to be equal to 1 over secant theta times secant squared theta d theta. Well, secant squared divided by secant is just going to be secant. And this isn't bad because, as we learned our last class, the antiderivative of secant is equal to the natural log of the absolute value of secant theta plus tangent theta plus c. But I can't stop just yet because I started with dx, which means I need to end it with x. And so we're going to do that. Secant theta, we know tangent. So I need to know what secant is. Well, I know tangent is equal to x, which again is like doing x over 1. Tangent is opposite over adjacent, which means my hypotenuse would be the square root of 1 squared plus x squared, so 1 plus x squared. Secant is hypotenuse over adjacent. Hypotenuse over adjacent would just be the square root of 1 plus x squared. So this becomes natural log of the absolute value. Secant, as we just said, was the square root of 1 plus x squared plus tangent, which we know is just x plus c. That one wasn't that bad, but again, if any of it doesn't make sense, please let me know. I will be more than happy to help you out. Another example. On example number 5. Integral of x cubed square root of x squared plus 4 dx. So same thing here. Since in here I have something squared plus a constant, I'm going to use my rule that 1 plus tangent squared is going to be equal to secant squared. But this time, since it's plus 4, I would let x be equal to 2 tangent because I want to square it and get a 4. So it's 2 squared, so 2. So the derivative of 2 tangent is 2 secant squared. So let's plug everything in. Integral. X cubed means I want to do 2 tangent, that whole quantity cubed. 2 cubed is 8, and then tangent cubed is tangent cubed, d theta. Square root of x squared, 2 squared is 4, so 4 tangent squared theta plus 4, and then dx we just said was 2 secant squared. Once again, this looks like a big old mess, but it probably works out really nicely. So let's see what happens. I have an 8 and I have a 2. 8 times 2 is 16, so let's factor out 16. Tangent cubed theta. What can I do in here? 4 tangent squared plus 4 would be 4 secant squared because of that trig rule from the start of class. And then secant squared again. Let's keep working. Tangent cubed, there's nothing I can do with that. Square root of 4 secant squared. Square root of 4 is 2, so I'm going to go ahead and bring out that 2, make this 32. Again, I got another 2 because the square root of 4 is 2, so brought it out front. Square root of secant squared is secant. Then we still have secant squared. Secant times secant squared is secant cubed. So this becomes 32 integral tangent cubed theta secant cubed theta d theta. And we can do this. In fact, we did one almost exactly like this whenever we did section 3.2 our last class, on the very last one of these. Remember, whenever they are both odd, I want to take out one of each. So this is going to be 32. Take out one tangent, and we're left with tangent squared. Take out one secant, we're going to be left with secant squared, which will leave me with one tangent and one secant. Why is this helpful? Because I know that the derivative of secant is equal to secant tangent, which I have, so that's really nice now. But what this means is I want tangent squared to then be written in terms of secant. We know that tangent squared is secant squared minus 1. So rewrite tangent squared as secant squared minus 1, which is with secant squared theta, tangent theta, secant theta, d theta. Now I can use u equals secant. So du is equal to secant tangent, which is going to make this 32 integral. Secant squared minus 1 is now u squared minus 1 times u squared. All of this becomes du. This isn't hard because now I can just distribute my u squared. 32 times the integral. U squared times u squared is u to the 4th. U squared times 1 is u squared du. Take the antiderivative of that. Add 1 here, gives me u to the 5th over 5. Add 1 here, gives me u to the 3rd over 3 plus c. Plug back in what we said u was, gives me, and then also distribute the 32. 32 secant to the 5th theta over 5 minus 32 secant to the 3rd theta over 3 plus c. But I still can't even stop there because I started with dx, which means I need it in terms of an x. I know x is equal to 2 tangent, which means tangent is equal to x over 2. So I need to use that and figure out what secant is. So if tangent is x over 2 and tangent is opposite over adjacent, that means my hypotenuse is x squared plus 4 because it's x squared plus 2 squared. So my hypotenuse is the square root of x squared plus 4. Secant is hypotenuse over adjacent. So secant would be square root of x squared plus 4 over 2. So rewriting that, you get 32 times square root of x squared plus 4 over 2 to the 5th over 5 minus 32 times secant we just said was square root of x squared plus 4 over 2 to the 3rd over 3 plus c. If you want to stop right here, I am perfectly fine with that. That is okay. Technically, I can reduce this a little more because 2 to the 5th is 32. So this is going to cancel out, leaving me with just square root of x squared plus 4 to the 5th over 5. 2 to the 3rd is 8. 32 over 8 is 4. So this would be 4 times square root of x squared plus 4 cubed over 3 plus c. But again, I'm okay if you want to just stop with this right here. That's perfectly fine. So I know I'm going through these kind of quick, but it's because I'm talking to nobody. And so, reminder, y'all can always stop, pause, rewind, all of that stuff. And of course, if it doesn't make sense, reach out and I will be happy to help you out. Have some more examples. For those following along on the handout, we're actually going to skip example number 6. And we're going to go straight to example number 7, which will be the last one we do. Example number 7 is the integral of dx over square root of x squared minus 4. So for this one, I have something squared minus a constant. The first ones we originally did at the start of class was a constant minus stuff squared. This is switched. This is stuff squared minus a constant. So this time I'm going to use my rule that says tangent squared theta equals something squared, secant squared in fact, minus 1. This follows more of this form because something squared minus a constant. So for this one, x would be equal to, I have a 4 there, which means I want to use 2. So 2 secant theta. Therefore, dx, the derivative of that, the derivative of 2 secant is 2 secant tangent d theta. So let's see what happens here. This is going to be equal to integral. Remember, I could put a 1 on top and bring this outside, which is what I'm going to do right now. Actually, I don't have to. I can just leave it there. It doesn't matter. Either way, it's fine. Dx we said was 2 secant theta tangent theta. D theta I'm going to write out front or outright. Square root of x squared. 2 squared is 4. Secant squared is secant squared. Minus 4. And let's simplify this and see what happens. It'll probably work out really nicely. So this is going to be the integral. Nothing I can really do on top. 4 secant squared minus 4 by our trig rule is actually 4 tangent squared. Once again, on top, there's nothing I can really do, so leave it there. Over square root of 4 is 2. Square root of tangent squared is tangent. Why is that really nice? Because 2's cancel out, tangents are canceled out. So this is just the integral of secant theta d theta, which we already know this. We've done this a few times now. That's the natural log of the absolute value of secant theta plus tangent theta plus c. But again, I started with dx, which means I want it in terms of the dx. So secant, we already know from this, secant is going to be x over 2, because if I divide by 2, so that part's easy. Plus tangent, though, if secant is x over 2, remember secant is hypotenuse over adjacent. So this is going to be the square root of x squared minus 4. So tangent is opposite over adjacent. So it's going to be the square root of x squared plus 4 over 2. So once again, the idea here is that it's going to be something that looks hard, which I'm going to turn into trig because I can work with that. I can work with trig stuff. And so that's what I want to do using our trig rules. So if any of that does not make sense, please just let me know.